In this lesson, we're going to look at the graphs of sinusoidal functions. A sinusoidal function is any periodic function whose graph has the same shape as the graph of y equals sine x. So it says, investigate the math. Students in Simone's graduating class went on an exchange trip to China. While they were there, they rode the Star of Nanchang, one of the tallest Ferris wheels in the world. Simone graphed the sinusoidal function that represented her ride. Now we can see the Ferris wheel, but we can also see the graph that she drew. We can see the title. We could see some key points here. We've got the height measured in meters. We've got the time measured in minutes, and we can see that sinusoidal pattern. Now the first question says, how can you tell from Simone's graph that the lowest part of the Ferris wheel is 2 meters off the ground? And when we look at the lowest points, or our minimum values, we can see that the y value is 2 for each of them. So the lowest possible value, the lowest possible height that she's going to be when traveling on this Ferris wheel is going to be 2 meters off the ground. B says, determine the maximum value of the graph. What is the height of the Ferris wheel? Well, similarly, we're going to be looking at the maximum points. And if we look at the maximum y value, we can see that's 160 meters off the ground. So that would be the highest point. And I summarized this below here. All right, the next questions are on the next page. So it says, determine the range of the graph. What does this value represent? Well, if we know that our minimum value is 2 and our maximum value is 160, then that's going to represent our range, right? 2 to 160. Now this can help us determine the diameter of the Ferris wheel. If we go back and look at the picture, right? If this here is my minimum value and this here is my maximum value, then the difference between my minimum value, which is maximum value, and my minimum value, 160 minus 2, would give me 158 meters. And that would be the diameter of our Ferris wheel. Okay? So that's what I'm referring to here, where it says our range is from 2 to 160. This can help us to determine the diameter of the Ferris wheel. It is the range of heights traveled by Simone as she goes around. D says determine the amplitude of the graph. What does this value represent? Well, let's go back again. The amplitude would be represented by the difference between the midline and the maximum, or the midline and the minimum. Well, the amplitude, it's very difficult to calculate without the midline, but we actually can do that. The formula that we can use to calculate the amplitude would be our maximum value minus our minimum value divided by 2. So in our case, that would be 160 minus 2 divided by 2. Okay? So if we go back to our notes here, right, our amplitude, our max minus our min divided by 2, and we get an answer of 79. And this represents the radius. Okay? So if we look here, right, 160 and 2, well, it's sort of hard to see there's the center. And because it's on an angle, it's not exact, but that would mean that this would be 79 and this would be 79. So that's giving us the radius of our Ferris wheel. Okay? For E, it says determine the equation of the midline. Similarly, we can calculate the equation of the midline using an equation. For this, I've done it graphically, just looking at the picture, and I can explain that. But our equation of our midline is always y equals, and that would be max plus min divided by 2. So in this case, that would be 160 plus 2 divided by 2, and that gives us 81. Now we can look at the picture on the other page, and we can see that this is the center of the wheel. So if I look at this picture again, right? So because we're 2 meters off the ground, that's 79, right? Up to here is 79. But if we want to know from the center all the way to the ground, that would be our 79 plus that extra 2. And that's where that 81 is coming from for the center of the graph. the center of the Ferris wheel. Now if we looked at that on our graph here, if we wanted to draw a line using a ruler, put your straight edge down and then draw that line in at 81. Well, that's very close to 80. We can probably move that up a little bit. So that would be at y equals 81. Make sure that that's as an equation, okay? All right, let's go back to the questions on the other page. So we're at the equation of the midline. We just finished E. So F says, determine the period of the graph. Explain your method. So period, when we're talking about period, we're talking about how long it takes for there to be one full cycle, okay, or one repetition of our graph. So if we look here, there's lots of different points at which you can calculate period. In this graph, I can see that my starting point is at 0, and then that point happens again 30 minutes later, and I can see that from the graph. And if I wanted to, let's say, choose a different point, I could start here and end here and see that the difference between 30 and 60 is another 30 minutes. Another place you can measure that is up here at the top, right? From one point to the next, that's the next time it repeats itself. The difference between 15 and 40 is 30. Any place you want where you can see a repetition, the difference between 20 and 50 is 30. So there's lots of places where you can measure period along your graph. Okay? So just to have a look at what we've done so far, period here is 30 minutes because from 0 to 2 to 32 is one cycle of the graph. So that's one example, but there's multiple places where you could have measured that. Okay, the last two questions, G and H. G says, what is the length of time needed for the star of Nanchang to make one revolution? Well, that's the same as our period, okay? So if you look here, for us to start, so if this is her starting point, she goes up to the maximum and back down to the bottom. Well, that's one full revolution once around. So that'll be 30 minutes again. And then the last question, how long does it take to get to the top of the Ferris wheel? Well, if it's 30 minutes to get all the way around, then it's going to be half the amount of time. And if we look here, we can see from 0 to our maximum, that's our halfway point, that's 15 minutes. Or if you want to go from the maximum down to the ground, then that is from 15 to 30, and that's 15 minutes again. So, whoops, I erased my line there. Sorry. There it is. Okay, so the question here, they're saying how long does it take to get to the top from the bottom, and that would be in 15 minutes. Okay, now let's try these out, these next couple of examples out. There's actually quite a few. There's 7 examples. Some I'll do with you, some I'll leave you to do on your own, and then we can go through those together. Example 1. The graph of a sinusoidal function is shown. Describe this graph by determining its range, the equation of its midline, its amplitude, and its period. All right, to calculate the range, we're just looking at the lowest possible point and the highest possible point. And we can see here that our lowest points are all sitting at y equals -3, and our highest possible points are sitting here at y is equal to 7. So our range would go from our lowest point, -3, to our highest point at 7. Our midline, the way we calculate that, we did that once before, we're taking our maximum plus our minimum divided by 2. So in this case, y would be equal to 7 minus 3 divided by 2, or y is equal to 4 over 2, which is just 2. So that's the equation of our midline. We can draw that in using a ruler or a straight edge. Oops. Draw that in at y equals to 2 and label that so we know that that's where that is. Now our amplitude is our max subtract our min divided by 2. So in this case, 7 subtract -3 divided by 2, which would be the same as 7 plus 3 divided by 2. That means our amplitude is 5, because that would be 10 divided by 2. Okay, and if you want to check, you could see from 2 to 7, the difference there, the difference there is 5. And if you want to go from the midline down, from 2 down to -3, then that's also 5. To calculate the period, you're going to see how the graph looks, and you're going to find where it repeats itself. So if I start at one point, like if I start at the very beginning here, I can see it's starting at degree 0, and then the next time it repeats itself would be at this point here. So what are we counting up by here? It looks like 60s, so that point would be 180 degrees. So the distance from here to here, in terms of the degrees, is 180 degrees. So the period would be 180 degrees. Like in the Star of Nanchang example, you could go from other places, but it's a little bit harder to tell in certain spots. Where the crosshairs lie, it's a little bit easier. So that would be from 60 to 240, and then you could do the subtraction there to find the 180. So wherever it's most convenient for the example that you're looking for. All right, take a look at example 2. In this case, we're given the parameters, and we have to draw the graph, which is a bit more challenging. Okay, so it says sketch the graph of a sinusoidal function with the following characteristics. The domain is between 0 degrees and 360. If you'd rather write the domain this way, you can do that. The range goes from -5 to 9. So remember, you don't have to write the domain and range that way, but you do need to be able to read that. The period is 120 degrees, so that means that there's one full cycle in 120 degrees, and the y-intercept is 2. So even though we want to go from 0 to 360, we only have a period is 120. So if I take 360 degrees divided by 120, I can see that I'm going to have 3 periods showing on my graph. So if that's 120, that's 240, that's 360. So that's where my graph is going to end. So in between 0 to 120, that'll be one cycle. 120 to 240, that'll be another one, and 240 to 360 will be another one. All right, the y-intercept is 2. My min is -5 to 9. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Just try to do your best to leave those evenly spaced. And the same in the other direction. Down to -5. That's our lowest point. And then 2 is important because that's our y-intercept. We can also figure out our median using our range. Our median line, y equals, and so we're going to add those 9 plus -5 all divided by 2, and that would give us a median line at y equals to 2. So let's draw that in. Okay, so our max and our min, this is a sinusoidal function. So if we're going to graph the function y equals sine x, we know from previous examples that goes from 1, -1. It starts at 0 and it goes up to 1 and down to -1 and then back here. And if one cycle is 360 degrees, then halfway is 180 degrees, and then it hits its maximum and minimum at 90 degrees and at 270 degrees. So we're going to draw this exact same graph, but we're going to shift it up so that instead of starting at 0, it's starting at 2. And then you can see it's built into quarters. So the halfway point, it's going to be at the same point as its starting point. So the halfway point from 0 to 120 would be 60. And that would be at the same point, and then again at the same point at 120, right? So those are those 3 key points. Now in between, you've got your maximums and your minimums. So halfway between 0 and 60 is 30. Between 60 and 120 is 90. So we've got our maximum at 9 and 30, and our minimum is at 90, and -5. So if we draw a smooth curve through this, we could see our sinusoidal function appearing. So that's one full cycle. And you're going to draw this again for 240. So another full cycle between 120 and 240, and then another full cycle between 240 and 360. So go ahead following the same pattern, filling in those angles and putting in those key points. Draw the next 2 cycles. I'm going to do that as well, but hit pause on the video, okay? So when I'm looking at your graph, I'm looking for those key points that are visible and that they're lining up with the angles as necessary. Make sure you label those graphs really clearly. Let's take a look at another example. In example 3, it says the graph of a sinusoidal function is shown. Describe this graph by determining its range, the equation of its midline, its amplitude, and its period. Alright, so we can see the range because we can see the maximum value here is at y equals 2, and the minimum value here is at y equals -4. So the range goes from -4 to 2. The midline, we get the equation, and we'll take our maximum, well, I'll just write it right in, maximum plus our minimum divided by 2, which gives us a midline of -1. You can draw that in here. At -1. Oops. Our amplitude be 2 minus -4 divided by 2, and that would give us an amplitude of 3, because that would be 6 divided by 2. And you can always check that, right? That's an easy one to check. Just count and make sure that that actually worked out. And now the period. So it kind of looks like the period would be 5, right? And you'd be right here. But it's hard to see that because your graph actually isn't repeating itself. So does it end at 4.5? Does it end at 5? Where is it ending? So we can see very clearly that half a period, if it starts at 0 here, half a period would be at the 2.5 mark, right? You can see that that's half a period. So sometimes if the whole period isn't shown, we know that another half period would be another 2.5. So if we do 2.5 times 2, that would give us a period of 5. 5 whats? Well, we're assuming this is measured in radians, but we're not really sure. Okay? So that's how we would figure out the period if the whole picture isn't shown, if the whole cycle isn't shown. Get what you can. Even if all you could get is a quartered period, then times that by 4. Alright, go ahead and try example 4 on your own, and then press play and check your answer. It's the same idea. Determine the range, amplitude, period, equation of the midline for the sinusoidal function. Alright, so checking your answer here, you should see the range goes from -1.5 to -0.5. You've got your equation for your midline, and I've drawn that in at y equals 1. Amplitude is 0.5, and the period you can see is 2. Alright, let's take a look at example 5. Now in example 5, we've got a scenario here. It says for a physics project, Morgan and Lily had to graph and analyze an example of simple harmonic motion. Morgan swung on a swing, and Lily used a motion detector to measure Morgan's height above the ground over time, as she swung back and forth. The girls then graphed their data as shown. At the end of each cycle, the swing returned to its initial position, which resulted in a sinusoidal graph. Interpret the graph. Now it's pretty vague when they say interpret the graph, but what they want you to do is find the range, the midline, the amplitude, the period, and then apply those values once you figure them out to the situation. Alright, so let's take a look at the range here. And we can see the range if we go every box is 0.2, I believe. So our range goes from approximately 0.8 to 2. Now the midline would be our max plus our min divided by 2. So that would be 2. Well, we have to do it as an equation. So y equals 2 plus 0.8 divided by 2, and that would give us an equation of 1.4. The amplitude is subtracting, so 2 minus 0.8 divided by 2, and we would get an amplitude of 0.6. And if we take a look at the period starting from the first swing to the first repetition, we could see the time would be 1.5 seconds. All right, so having a look at our data here, well, maybe we should draw in our midline. We can see that the highest point the swing gets to is 2 meters above the ground. The lowest point when the swing is at rest, or even when it's at the lowest point on that downward swing or that upward swing, we're only 0.8 meters off the ground. And then the amplitude, so that tells you the difference in resting point to your highest point, or the difference in your resting point to the lowest point. And then our period is how long it takes for you to take one full swing from up to down. And then our midline is that halfway point, right? The halfway point in between. So let's write this down and summarize all of our findings. It takes 1.5 seconds for one complete swing. The max height of the swing is 2 meters and its minimum height is 0.8 meters. B says determine Morgan's height above the ground at 4 seconds. Well, we can interpolate that right off of our graph. So if we take our ruler, draw a line up from 4 seconds to where it meets our graph, you can see that that's going to touch right about there. And then if we draw a line across, this is how you're going to show your work. Draw a line across, we can see that she'll be 1 meter above the ground. So for B, her height above the ground is 1 meter. Okay, let's take a look at example 6. In example 6, it says, to collect different data set, Lily swung on a different swing, and Morgan created the graph to the right from the data she collected. Interpret this graph and compare the two swings. So I'm going to let you take a stab at this, so go ahead and try them out, and then come back and check your answers with mine. So the range is from 0.8 to 2.5. The midline is y equals 1.65. Amplitude 0.85. That's not a y equals, I'll correct that. Just equals 0.85. We don't need an equation for the amplitude. The period is 2 seconds. And then B asks us to compare the two swings. So the second swing goes 0.5 meters higher than the first, so the midline changes from 1.4 meters to 1.65 meters. The amplitude is 0.25 meters greater, and the period is 2 seconds, not 1.5 seconds. So it takes 2 seconds for one complete swing, and the maximum height is 2.5 meters. All right, let's take a look at the last example. In example 7, it says Alexis and Colin own a car and pickup truck. They notice that odometers for the two vehicles have different values for the same distance. As part of their investigation into the cause, they put a chalk mark on the outer edge of a tire on each vehicle. The following graphs show the height of the tires as they rotated while the vehicles were driven at the same slow, constant speed. What can you determine about the characteristics of the tires from these graphs? So you can see from the two graphs, they're both graphing time and height of the tire in inches. So go ahead and figure out the information for both of these vehicles and see what you can determine. Come back and check with my answers once you're done. So I made a bit of a chart comparing my data here. So here's the information for the car and the truck. We know they both have a minimum of 0 because the tires move along the ground. So if we look at our graphs here, the minimum for both of them is right at 0. Now, the maximum is 24 inches for the car and 32 inches for the truck, and that actually corresponds with the diameter of the tire. The midline is 12 for the car and 16 for the truck, which corresponds to the radius of the tire. The period is 1.2 seconds for the car. So if we think about that, that means one revolution takes 1.2 seconds, whereas the truck is 1.6 seconds. So it's covering, right, more space in less time. So the truck tires take longer to make one revolution. The truck travels further with one tire revolution. So there's lots of information using these graphs that we can actually figure out. So that's the last example, but there's a really nice summary on the last page here. If you have a look, we've got our equation for our midline. We've got our equation for our amplitude. We've got a nice graph that summarizes all the different terms that we've been looking at. That's it for today's lesson. Thanks for joining me.